Let's now learn about what a linear programming problem is, and in short it's called an LP problem. Now, an LP problem start out with a given function being a linear function in two variables. So I'm going to start out by letting a function f xy be x plus 5y. For short, a lot of time you might see the entire f of xy right here is being substituted by a different variable's name. It could be a z. So the same function expression could be written as z as a function equals x plus 5y. So this function that we're looking at is called, this is an example of a linear function in two variables. So first of all, let me explain about being a function in two variables. So our f of x, y here, or for short, z equals x plus 5y. This function is being a function in two variables, means if you're simply substituting into the function only a value for x and without giving the value for the y variable, then we won't know. So only knowing one value. So if we only know x equals 1 without knowing the value of y, then we won't get an output. And so to get an output, we need to know both values of x and y. So here, let's say, for example, when x equals 1 and y is given to be 3, then my function reads the output as the value for z is going to equals, so let's say the coefficient of x is 1, so 1 times 1. So now with the substituted value of x equals 1, we substitute that in here, and the function output or the value of z also depends on the value of y as given. So here for our y variable, we multiply y by 5 according to the function. So 5 times y substituted by 3. So our function here in the end has output. The value for z equals 1 plus 15, 16. And so what I just demonstrated here is for a function being in two variables, it means the output, the final value of the function, depends on two values of two different variables. And that's what it is right here. So in this case, I show a calculation of the output value for z when x equals 1 and y equals 3. So now you know that our function here is a function in two variables. But now, what does it mean by being a linear function? So allow me to also explain that. So linear function in a more general concept, in a more general understanding. Let's say your function here is in two variables, and x and y are the two variables that's responsible for the output. Then your function, being a linear function, it is required that each variable here can only be multiplied with a coefficient. So it's in the form of an ax, some coefficient multiplied with x, plus some coefficient multiplied with y. No power. If it's a square on any of with the variable, it's not a linear. If there is a square root with any of the variables involved, it's not a linear function. So strictly as a requirement, the linear function can only have a coefficient, could be negative, could be 0, but a coefficient multiplied with the first variable plus another coefficient multiplied with the next variable. And so in this fundamental form of being a linear function of two variables, then our function here is clearly a linear function. For z equals x plus 5y, the variable, the coefficient for our x variable is 1, and the coefficient for in front of our y variable is 5. And once again, each of the variable here, each term of the variable does not have any special powers other than just power 1. And I also need to clarify, in case we have a function like this, z equals x times y, and with a coefficient. Now, so this function is not a linear function. This function of ours right here, once again, it has the two variables. So it's a function of two variables. It has a coefficient, but now the two variables are being in a product. Difference with what we see in here as the function is being one coefficient multiplied with one single variable and another coefficient multiplied with one single variable. So here is two variables standing on two separate terms. That's what makes it linear. This is not a linear function. So now, knowing that our function here is a linear function in two variables, then in theory, or theoretically, in the entire x and y plane right here, let's say I already chose one example when we have a point x equals 1, y equals 3. This pair of values, graphically speaking, is a point in the x and y plane. And this point was, this pair of values, or graphically as a point here, was an input pair of value for our function z to get an output. And so if we think of another pair of values, let's say here, -2, 1, then we have another pair of value to substitute into the function here. So here, if our point is at -2, 1, for -2 for x, 1 for y, then we have our z value equals -2 plus 5 times 1 substituted by y, and our z value here comes out being 3. So what I'm trying to point out is that, so technically any point in the x and y plane existing as a pair of value, x and y, so any point here, and in formal math term, each quarter of the entire plane here is called a quadrant. So any point throughout the entire x and y plane right here can be an input pair of values for any linear function. And so at the bottom line right here, the domain is the domain for any linear function in two variables. It's going to be all pairs of values, x and y. And so realizing that any function, any linear function in two variables has such a large domain, I just now said that the domain for any linear function, this function or any other linear function in two variables, there are domains simply being all pairs of x and y values. So this is a very large domain. And so realizing the nature of how big the domain for any linear function in two variables is being that big. So usually in our kind of application, usually in our type of problems that we're doing in our class for business math, then a lot of time, instead of working after a linear function in two variables is given to us, then the domain is usually being restricted. And you can see that I'm using the term restricted. Formally speaking, a lot of time once the function is given, then your problem always comes with a description such as, so here's your function, linear function in two variables, but it comes with a description saying your function here is subject to, and then here it comes with a few inequalities. So let's say here I'm going to have, in this video lecture here, how about x plus y being less than or equal to 25, y is greater than or equals to 10, and minus x plus 2y is greater than or equal to 0. So what is the meaning of having something like this? And as I already said, so in our type of problems that we're doing in math for business, then a lot of time when once we have a linear function in two variables given to us, then it will always come with a requirement or a restriction saying that an informal term, formally worded, it says subject to, so after a function is given, it's subject to, and it has a few inequalities being listed here. And notice we've seen these linear inequalities here previously in our other example, in our other video lessons. So what are these inequalities doing to our function, to our linear function in two variables here? So along with what I said earlier, since the domain is being too big, technically, or in theory, the domain for any linear function in two variables can take all pairs of x and y values. And so the idea now is that in business application, we don't want to take all pair of values of x and y, but instead we only want to restrict, we want to limit our domain to only a certain region. And so these are, so the way I see it here is that we don't take all values of x and y, we only take those values of x and y where it satisfies x plus y must be less value or equals 25. And the x value, we only want that to be greater than or equal to 10. And simultaneously, it's also required that our xy pair of values satisfy minus x plus 2y greater than or equal to 0. So in other words, this is the way how it's formally written, but we understand these as the constraints. So this inequality, that second inequality, and the third inequality here, all three of them together are being referred to as constraints. So, simplest way to put it, a constraint is something that limits the values of x and y, because a pair of x and y now is an input pair of value for our linear function in two variables. So being a constraint limits how we choose the input value, the input pair of values for our function. And now if we're looking further, all of these constraints together, learning from our other video lessons on a solution to a system of linear inequalities, then all of these constraints together, and in some other problems, some function might come with even more than these constraints right here. So here we have 3 constraints, but some other problem have 4 or 5 constraints here, but they're all in the form of some inequality of some kind. But in the end, all constraints together are being put as a system of linear inequality. And so after the reminder that these inequalities together is giving us a system of linear inequalities, then at this point you can go ahead and pause the video and quickly find the graphical solution, the graphing solution as a region that satisfy all these three inequalities before I actually show it myself here. Alright, so at this point I hope you now have your own thoughts a little bit in terms of what's the graphical region or what's the graphical solution to this system of inequalities altogether. So in my graphing space here, let's say each square grid here represents a 5. So vertically, that's vertical space here is a 5. This horizontal grid here, the space there is a 5. Then x plus y being less than or equal to 25, provided you have seen some of my other videos showing how to graph the solution to an inequality, one single linear inequality in two variables, then this is our line representing that equation, x plus y equals 25. And of course, since the inequality had equal signs, we are using the solid line here. And according to what we've learned in the video lesson on graphing the solution to an inequality, linear inequality, we're shading below this area. So here's our line again. And I'm going to need to make it a little thicker. The next inequality in our system is x greater than or equals to 10. Have a moment thinking of that for yourself. And so this line, very heavy line right here that I'm using to make it a little more stand out compared to my other shading sketch, then this line right here is our line for x equals 10. And of course we want x to be greater than or equals 10. So this line is a solid line and we are shading to the right hand side of it. And so now you can see that the area down here is the area where we have a double shading, the two regions being double shaded. And then go ahead and start thinking about the solution, the sketch solution to the third inequality, minus x plus 2y greater than or equal to 0, before I had a chance to put it up. And this third line that I just now put up right here is the line representing the equation minus x plus 2y equals 0. And of course, the shading of the region that satisfy this inequality is to be shading above. Now I'm going to be shading above that line. So the picture now becomes a little busy, but the region that satisfied all of these three inequalities together is now in here, inside of that little triangle. And now allow me to rescale my graph here so that each of the two little square space, so one big square space like this, is a unit of 5 here. And once again, these are the three lines. This is the line x equals 10. This line is the line x plus y equals 25. And this other line right here is minus x plus 2y equals 0. Then the sketched solution, the graph solution of our system inequalities here earlier is now in a bigger picture. And it is only that region being inside of this part right here. And so the idea now is that instead of taking the entire, remember the entire domain to any linear function of in two variables is technically the entire x and y graphing system right here, the entire plane of x and y coordinates. But now, since now we're having constraints, and the good thing about constraint now is that it limits down. All constraints together limits our input pairs of values into within this region only. And so, as I just said, we now only gonna take x and y values, pairs of x and y's value being inside. Now we only choose inputs x and y from inside of that region only. And that's why when we were learning in the other video lessons about how to graph the solution of a system of linear inequality, I briefly mentioned that term, that this region here is called a feasible region. But without being able to explain much about why it's called a feasible region. But now, once we're seeing the application, because this is the purpose of coming up with the solution, a graph solution to a system of linear inequalities. A system of linear inequalities limits down the inputs, pairs of values for any of our function into variables. And so that's why it's called feasible regions, meaning these are the only possible region that we can choose our input values, that we can select our inputs pairs x and y from, in order to substitute it in and calculate in our linear function of two variables. And so, just like how we have done that before, then any feasible region, or the graph region, the graph solution to any system of inequality, consequently comes out with these, what I so-call any of these is a corner point. So we have these corner points right here. So this region, according to our three inequality, has three corner points. So the corner points are 10, 15 right here. That's one corner point. We have right here this corner point being 10, 5 being another corner point. And the last corner point right here takes a little more steps, but you also learned that in the other video lessons. But this corner point right here is at 50/3 for x and 25/3 for y. So we have three corner points.